There is a model running on a phone in someone's pocket right now that can do things which 3 years ago required a data center full of GPUs and a multi-million-dollar training run. It answers questions, it writes code, it summarizes documents, and it does this on a chip that fits in your hand, drawing less power than the screen it renders to. That model did not learn everything from scratch. It learned most of what it knows from a much larger model that already paid the cost of figuring things out. The big model did the expensive thinking. The small model copied the answers. This is the trick that quietly reorganized the entire economics of artificial intelligence. We spent years in a race where the assumption was simple: bigger is better. More parameters, more data, more compute, more capability. And that was true, right up until someone figured out how to take the capability out of the big model and pour it into a small one for a tiny fraction of the cost. The frontier labs spent hundreds of millions of dollars climbing a mountain. And then a generation of much cheaper models showed up at the summit, having taken a chairlift that the expensive climbers accidentally built for them. The name for that chairlift is distillation, and it is one of the most important and least understood ideas in the field because it touches everything from how you deploy models cheaply to the lawsuit risk sitting in a frontier lab's terms of service to the question of whether the company spending billions on training can ever actually defend what they built. I am Mo, and this is the Practical AI Digest. Today we are talking about knowledge distillation, how small models eat big models for lunch, and what that means for everyone trying to build with AI without a Frontier Labs budget. Let me start with what distillation actually is, because the name is a good metaphor but a bad explanation. The core idea comes from a 2015 paper by Jeffrey Hinton, Oriol Vinyals, and Jeff Dean titled Distilling the Knowledge in a Neural Network. Three of the most consequential names in the field on a single short paper that turned out to matter enormously. Here is the setup. You have a big model. Call it the teacher. It is accurate, it is capable, and it is expensive to run. You want a small model, call it the student, that behaves as much like the teacher as possible, but costs almost nothing to run. The naive approach would be to train the small model on the same labeled data the teacher was trained on, but that does not work very well. The small model just does not have the capacity to learn the raw task as well as the big one did. If learning from the raw data were enough, you would not have needed the big model in the first place. Hinton's insight was that you should not train the student on the original labels at all. You should train it on the teacher's outputs, and not just the teacher's final answer, but the full probability distribution the teacher produces over all possible answers. This is the part that matters, so let me slow down. Imagine you show an image classifier a picture of a dog. The correct label is dog. A normal training signal says the answer is dog with 100% confidence, and everything else is 0. But the teacher model does not actually think that way internally. The teacher might output 90% dog, 7% wolf, 2% cat, and a tiny sliver on fox. That distribution contains information that the single word dog throws away. It tells you that a dog looks a lot more like a wolf than like a cat. It encodes how the model understands the relationships between categories. Hinton called this the dark knowledge. It is the structure hidden in the probabilities that you never see if you only look at the top answer. The argmax, the single most likely token or label, is the tip of the iceberg. The shape of the whole distribution underneath is where the teacher's real understanding lives. When you train a student on those soft probability targets instead of hard labels, you are not just teaching it the right answers. You are teaching it how the teacher thinks about the space of possible answers. And it turns out a small model can absorb that structure far more efficiently than it can rediscover it from raw data. That is the whole trick at its heart. Soft labels carry more signal than hard labels. The student learns the teacher's worldview, not just the teacher's verdict. Some distillation methods go further and match intermediate representations too, lining up the internal layers of the student with the internal layers of the teacher. So the student learns not only what the teacher concludes, but something about how it gets there. But the foundational idea is the soft targets, and that idea has held up for a decade. Now let me make this concrete with the model that proved distillation works at scale. In 2019, a team at Hugging Face released DistillBERT, a distilled version of Google's BERT, which at the time was the dominant language understanding model. DistillBERT was roughly 40% smaller than BERT and ran roughly 60% faster. And the part that made people pay attention. It retained around 97% of BERT's performance on the standard language understanding benchmarks. Cut the size nearly in half, run it substantially faster, lose 3% of the capability. For most production systems, that is not a trade-off. That is a free lunch. DistillBERT went on to become one of the most downloaded models in the world, precisely because almost nobody actually needs the last 3% if it costs them double the compute. That is the pattern that repeats across the whole field. You very rarely need every last point of capability. You need most of it cheaply, fast, and ideally on hardware you control. Distillation is the technique that delivers exactly that shape of value. And the same shape shows up again in the world of small open language models. TinyLlama, a model with just over 1 billion parameters, was trained to capture a meaningful slice of what much larger language models can do, small enough to run comfortably on modest hardware. The whole genre of small, capable open models that exploded over the last 2 years rests on the same foundation. You take the expensive understanding that lives inside a large model, and you find a way to move as much of it as possible into a package that an ordinary developer can actually afford to run. The story is always the same. The teacher is heavy and the student is light, and the art is in losing as little as possible in the transfer. Let me talk about why a small model can match or even beat a big one on a specific task, because this surprises people who think of capability as a single number. A large general-purpose model is a generalist. It has spread its parameters across an enormous range of abilities, most of which you will never use. If your actual task is classifying support tickets, or extracting fields from invoices, or answering questions about your product documentation, you do not need a model that can also write sonnets and debug Rust. You need a model that is excellent at your one thing. When you distill a large model down to a small one focused on a narrow task, the student can spend all of its limited capacity on that task. And a small model that is fully specialized on a narrow problem will frequently outperform a giant model that is only paying partial attention to it. The generalist knows a little about everything. The distilled specialist knows your problem cold. This is the distinction between general-purpose distillation and task-specific distillation, and it is worth holding clearly. General-purpose distillation tries to compress the teacher's broad capability into a smaller but still broadly capable student. That is hard, and you usually do lose something. Task-specific distillation throws away everything except the slice you care about, and on that slice, the small model can be astonishingly good. Most of the value companies actually capture from distillation comes from the task-specific side, not the dream of a tiny model that does everything. Now we have to talk about the controversy, because in early 2025, distillation went from a quiet engineering technique to a geopolitical news story. DeepSeek, a Chinese lab, released a family of models, including reasoning models that perform shockingly well for their cost. Alongside their flagship, they released a set of smaller distilled models, built on open bases like Qwen and Llama, that inherited a remarkable amount of reasoning capability. The models were genuinely impressive and genuinely cheap, and the market noticed in a very loud way. Then came the accusation. OpenAI and others suggested that DeepSeek may have distilled from OpenAI's own models. The idea is that you can perform distillation through an API. You do not need access to the teacher's weights or its internal probabilities. You just send the proprietary model an enormous number of prompts, collect its outputs, and train your student on those outputs. The big model becomes an oracle you query at scale, and the answers it gives away become your training set. This is sometimes called black box distillation because you never see inside the teacher. You only see what it says. Here is where it gets thorny, and I want to be precise rather than take a side, because the facts and the law are both genuinely unsettled. Almost every Frontier Labs terms of service explicitly prohibit using their model's outputs to train a competing model. So if you did this, you would be violating a contract. That is reasonably clear. What is far less clear is whether model outputs are even copyrightable, whether training on them is infringement in any legal sense, and whether a terms of service clause is enforceable against a party in another jurisdiction who never agreed to it. There is real irony here, and it is worth naming plainly. The Frontier Labs trained their own models on enormous quantities of data scraped from the open internet, much of it under exactly the kind of dispute about consent and fair use that they are now invoking against people who train on their outputs. The companies most upset about distillation are companies whose own training data provenance is, to put it gently, contested. I am not going to pretend that resolves the ethics, but you cannot discuss the morality of distilling from a model without acknowledging how that model was built in the first place. This connects to a broader and more legitimate practice that powers a huge amount of modern model building, which is synthetic data generation. Distillation through an API and synthetic data generation are, technically, almost the same act. You use a strong model to generate training examples, and you train a smaller or newer model on them. Microsoft's Phi series of small models lean heavily on this approach, built around the idea of training on textbook quality data, much of it generated or curated with the help of large models rather than the raw chaos of the open web. The result was small models that punched dramatically above their parameter count on reasoning and coding tasks. Google's Gemma models have used distillation from larger Gemini family teachers as an explicit part of their training. The entire open weight ecosystem around Llama is shot through with fine-tunes trained on data generated by GPT-4 class models. Synthetic data, generated by a strong teacher, is now a standard ingredient. The DeepSeek fight is not about whether this technique is legitimate. The technique is everywhere. The fight is about whose teacher you are allowed to use, and under what terms. Let me put the cost equation in front of you, because it is the whole reason any of this matters. Training a frontier-scale model from scratch is a project that costs many millions of dollars in compute alone, before you count the research talent and the failed runs. Distilling a small, capable student from that teacher costs thousands, sometimes less. The asymmetry is staggering. The party that did the hard, expensive work of pushing the frontier captures a fraction of the value, because once the capability exists in any accessible form, copying it is several orders of magnitude cheaper than creating it. Climbing the mountain costs a fortune. The chairlift ride to the top costs lunch money. That asymmetry is the thing that should worry anyone running a frontier lab, and it leads directly to the strategic question. If frontier capability can be distilled into cheap, small, open models shortly after it appears, what exactly are the frontier labs selling? They spend the enormous sum to reach a new level of capability. Within months, distilled and synthetic trained models approximate a large slice of that capability at a tiny cost. The moat, if there is one, is not the capability itself. The capability leaks. The moat has to be something else. The speed at which they reach the next level before the last one gets copied. The reliability and safety scaffolding around the raw model. The distribution, the enterprise contracts, the integration. But the raw intelligence, the thing they spent the most money on, is the part that is hardest to defend, because distillation makes intelligence portable. That is an uncomfortable business model. You are running on a treadmill where your most expensive asset depreciates the moment your competitors can query it. Now let me be the skeptic, because I do not want to leave you with the impression that small models simply win and the big ones are obsolete. They are not, and the places where distillation fails are extremely instructive. Distillation transfers what the teacher already knows. It does not create new capability. If your task requires genuine novel reasoning, working through a hard problem the teacher itself finds difficult, the student will inherit the teacher's struggles, not transcend them. On complex multi-step reasoning, on truly novel problems with no template in the training distribution, on tasks that require holding a large amount of context and reasoning over all of it at once, the small distilled models still fall short. There is a real and persistent gap between a distilled 7 billion parameter model and a frontier model on the hardest reasoning benchmarks, and that gap is not an accident. Reasoning depth appears to genuinely require capacity. You can compress knowledge efficiently. You cannot compress hard thinking the same way, because the small model simply does not have enough room to run the long internal computation that hard problems demand. So the honest framing is this: distillation is devastatingly effective for transferring known competence into a cheap package. It is much weaker at transferring the frontier's edge, the ability to handle the genuinely hard and genuinely new. And there is one more failure mode that hangs over the whole field, and it is the one I find most interesting. It is called model collapse. If you train a model on the outputs of another model, and then train the next model on the outputs of that one, and you keep going, generation after generation, the quality degrades. The rare cases, the tails of the distribution, the unusual but valid patterns get smoothed away a little more each round. A 2024 paper in Nature demonstrated this recursive degradation clearly. Models trained on too much model-generated data start to forget the diversity of the real world and converge toward a blander, narrower, more confident, but wrong version of themselves. Distilling from a distilled model eventually produces mush. The signal that originally came from real human data thins out with every copy. This matters more than an academic curiosity, because the open internet is filling up with model-generated text right now. The training data of the future is contaminated with the outputs of the present. If you are not careful about provenance, you are no longer distilling from a strong teacher who learned from reality. You are distilling from a photocopy of a photocopy. The labs that maintain access to genuinely human, genuinely diverse data, and that are disciplined about not poisoning their training sets with recycled model output hold an advantage that is quiet but real. In a world where everyone can distill, the scarce resource shifts. It is no longer raw intelligence. It is uncontaminated ground truth. So let me bring this back to where it lands for you if you are actually building. Distillation is not a niche research trick. It is the default path to deploying capable AI cheaply, and you should reach for it whenever you have a clear, bounded task and a strong model that already does it well. Use a large model to do the hard reasoning, capture its behavior on your specific problem, and train or fine-tune something small that you can run on your own hardware at a fraction of the cost and latency. For the vast majority of production tasks, a well-distilled specialist will serve you better than an expensive call to a frontier API. Reserve the frontier models for the genuinely hard, genuinely novel reasoning where the small models still cannot follow. And watch your data provenance like it is a security boundary, because in the age of distillation, the question of where your training signal really came from is no longer a footnote. It is the whole game. The big models did the expensive thinking. The small models are eating their lunch. And the most interesting question in this field is no longer how to build the biggest model. It is who gets to keep the value once the capability inside it can simply be copied. I am Mo Buyen. This has been the Practical AI Digest. See you in 2 weeks.